Now that we have a few useful reactions under our belts, it's time to put them together to think about synthesis, the process of making molecules. Why is synthesis so important? Taxol, a cancer drug, gives a prime example. Taxol was originally harvested from the Pacific yew, but it didn't take long before all the Pacific yew was close to being used up. People turned to synthesis, but it's a difficult molecule to make. It took 35 reactions to make Taxol in the first synthesis. That makes the drug incredibly valuable. It can't be harvested from natural sources, and synthesis gives access, but it's really expensive. It's so expensive that now it's created through natural mechanisms introduced into bacterial hosts. Synthesis, in the sense of organic chemistry, always involves specific chemical reactions, called synthetic steps, to reach a desired synthetic target. We draw out synthetic steps a little differently than we draw out mechanisms. Mechanisms only include the active species, which often aren't added in isolation. A synthetic step includes all reagents in the form in which they are added. In this example, bromide is used in the mechanism, but we indicate potassium bromide in the synthetic steps. In both cases, we leave out the potassium tosylate that is formed as a byproduct. Reagents can be listed as a separate reactant added with an arrow. However, in most cases, the new reagents are just listed on top of the arrow. Solvents, temperature, time, and other conditions are listed below the arrow. Sometimes a single reaction takes place with multiple distinct steps. When this is the case, numbers are listed before the reagents that are added as discrete steps. So in this example, we have sodium hydride first, and then we have methyl iodide afterwards. If conditions are specified for a multi-step reaction, they are often written directly after the reagent, separated by a comma or a slash. In this example, the first step uses DMSO as a solvent, and the second uses water as an added solvent. We can generally place reactions into two categories. Reactions that swap one functional group for another, called functional group conversions or transformations, and reactions that change the carbon skeleton. These are the distinguishing factors between the two tables at the end of each chapter. The example shown here uses reactions that you already know to accomplish a synthesis. An alkene can't readily form carbon-carbon bonds, so it is converted to an epoxide, that's a functional group conversion, before reacting with a Grignard reagent, which would be a carbon-carbon bond or a skeleton-changing reaction. The resulting alcohol is converted to a bromide, so a functional group transformation, which can be more easily replaced by an SN2 reaction with cyanide to form a new carbon-carbon bond. We don't typically start from a random molecule and try to turn it into a synthetic target, but instead we think about the target first and try to figure our way back to a molecule that might be a good starting material. This process of thinking about reaction schemes backwards to develop a forward synthesis is called retrosynthetic analysis, and it won E.J. Corey the 1990 Nobel Prize in Chemistry. Starting from the target, individual reactions are thought of as transforms, the undoing of a single reaction. An open arrow, as shown in this slide, indicates a transform from the target to the precursor. Usually, we have some sort of constraint that guides our retrosynthetic analysis. Most chemists give themselves the constraint that they must start from things that they can buy. But most undergraduate chemists will not have much of an idea of what can be bought. For undergraduate problems, we usually say that we should start from molecules of 3 or fewer carbons, sometimes offering specific exceptions like benzene. This is to approximate commercial availability without forcing you to look up every molecule you may want to use. This has the practical implication that we generally need to think first about how to form carbon-carbon bonds. In this reaction, we can think of the alkyne as a potential breaking point, since we know that we can make alkynes nucleophilic. Even though we could break on either side of the alkyne, the disconnect between carbons 3 and 4 would give us a chain of 3 carbons, whereas a break between carbons 1 and 2 gives us the disallowed chain of 4 carbons. Could we make that chain from something else smaller? Probably, but why go there when we don't have to? That gives us one side of the chain. If we want to use an alkyne as a nucleophile in a substitution reaction, the other side needs a leaving group. I like bromine. So apparently does your book. The larger molecule still contains 4 carbons, but on different sides of an ether. We've actually done a number of ether syntheses, but the best option for this is the Williamson ether synthesis, where we make one side a nucleophile and have an electrophile on the other side. In this reaction, it doesn't matter which side is which because no eliminations are possible on either side. At this point, we've identified all the steps required to make our target from molecules with 3 or fewer carbons. For a synthesis, we just need to put these back in the right order and add the reaction conditions. When we create a synthesis, we need to look out for synthetic traps. A synthetic trap is exactly as it sounds. A reaction looks like it will work, but we forgot something and a different reaction will happen instead, or we'll end up with a different regiochemistry than we expected. We want to first look for some ways to rearrange the synthesis to avoid the trap without reworking the whole synthesis. A common minor change is reordering a few steps. Sometimes, to get the right regiochemistry or stereochemistry, we need to add a special reaction. For example, we might need to add an alcohol to get the anti-Markovnikov regiochemistry that we want, then convert to better leaving groups. But sometimes the synthesis needs to be reworked completely because it's a trap. One type of synthetic trap is when we have multiple reactive functional groups. We might think about dividing these molecules into an alkyne nucleophile and a chain that has a leaving group and an alcohol. That's a bad idea though, because proton transfers are very fast and alkyne salts are very basic. We'll end up with none of our desired product because it's a trap. We also have lots of traps possible for reactions that give different regiochemistry. We could think about forming the alkyl halide by HBr addition to the alkene, but the bromine will end up in the wrong location with this, or any other alkene due to Markovnikov addition and the carbocation rearrangements. It's a trap. There are sometimes multiple options to solve a synthetic trap. One option for the reaction we just looked at is to use a regioselective hydroboration oxidation, then convert the alcohol to a bromine. That's what is shown. Other reactions, we can take care to pay attention to the type of control we are under to differentiate kinetic and thermodynamic products. That's one reason why understanding mechanisms is so important. Solvents, too, can help make sure we get intended products. Some solvents are reactants themselves, particularly polar protic solvents like water or alcohols. For example, we might think about a relatively straightforward reaction to get a trans 1,2-dibromo compound from an alkene. But if we use water as a solvent, we'll end up with a halohydrin instead of the desired product. Here's another example where the choice of solvent makes a big difference. Suppose we look at the transform shown and decide that we want to make an ether through substitution. We might choose water as a solvent because it's cheap and it's on tap, but we have to worry about the competing proton transfer. Instead, we'll choose an isopropyl alcohol as a solvent. This means that even though we might have to compete with a proton transfer, the product is the same as the reactant, and we can eventually go through the intended substitution. When we talked about stereochemistry originally, we went through a list of drugs, identified stereocenters, and talked about the need for enantiomer drugs to reduce side effects. Here's another example. The S enantiomer is marketed as a leave. If we want to make a leave, we need a stereoselective set of reactions. Targeting just the S enantiomer is an example of an asymmetric synthesis. This is a huge area of chemistry, but the very simplest level indicates that we need to focus on bimolecular reactions that preserve or invert stereochemistry. One trick to get the right stereocenter is to invert an alcohol by changing it to a halide. This makes it a better leaving group, and it also allows for a second nucleophilic attack that will give us back the original stereocenter that the alcohol had. Some of our reactions only add syn, particularly when we form rings. So examples of those would include our diazomethane reaction to form a cyclopropane, our metachloroperoxybenzoic acid to form an epoxide, and our hydroboration oxidation to form an anti-Markovnikov addition of an alcohol. Other reactions will only form anti. For example, our halogenation reaction, which gives us trans bromides, or our hydrohalogenation, which gives us a trans alcohol to a bromide. Even though on paper we can often get to a product no matter how many steps we take to get there, there are real considerations for real reactions. A good synthesis will keep steps to a minimum and keep yields to a maximum. This table explains why. Even if you have a very good yield for a single reaction, any losses are carried through to the next step. So a 5-step reaction with 90% yield at each step actually ends up being close to 60% overall. If you do that 4 times for a total of 20 steps, now your 90% looks a lot more like 12%. And look what happens to a 70% yield over 20 steps. Sometimes we can't do anything to change the percent yield for reactions, and we can't do anything to change the number of steps that we need to take. A final strategy that we use to preserve yields is called convergent synthesis. If we can create 2 pieces of the molecule separately, then join them later, the yields for the same number of steps are much better. Take a 7-step synthesis with 80% yields at each step. At the end of a linear synthesis, the yield is 20-some%. But if we do 7 steps as a convergent synthesis, even though our yields for each step haven't changed, our longest chain is 5 steps, and we end up with some 40% for a yield.